Alright, today we're going to determine the rate law for a given higher order reaction using the appropriate lab data. So we have a couple bits of notes on rate laws. We're going to distinguish between zero, first, and second order. And then we're going to do a couple examples. The quest that goes with this play posit is Kinetics Rate Law. So when we determine a rate law, on the last play posit we talked about relative rates. The rate law is specific to a reaction and typically only looks at the reactants. The first step is to determine the form of the rate law, especially its order. When we talk about order on the next slide, we'll be able to relate how the concentration affects the rate. It's always determined from experimental data. There are a couple different ways we can describe this process. If you hear the terms differential rate law, or just rate law, or the rate expression, they all mean the same thing. And that is this, right here. The rate is equal to K. K is a rate constant, and that is times the concentration of our reactant or reactants. And a reminder that the rate for a reactant is negative delta of your substance A, of the concentration of A, divided by delta T. So it's the change in concentration over the change in time. Now, this is a lowercase a, and oftentimes you might see me write it in cursive like that. That lowercase a is really important. If you write a capital K, it can be confused for one of two things. It could be Kelvin or the equilibrium constant. They are very, very different things. I know it's super, super annoying that they use K for so many different things. Why can't they just choose a different letter and make things easy on us? I know when I first was learning kinetics and rate laws, when we saw that, I was like, really? Like, why? It just makes no sense. Why do we just pick a different letter? There's 26 of them. Why? But I digress. It is what it is. The rate constant, its whole purpose is to cause the units of for your concentration to cancel out and to give you a rate in some sort of time unit. It is temperature dependent. And the units usually change depending on the order. If we have several reactants, and those reactants, their concentrations are in terms of molarity, well, molarity times molarity gives you molarity squared. So you would want those things to cancel out. So K in that particular instance would have units such that it would cause the molarity to cancel, and you'd be left in seconds or minutes or hours or whatever the time unit is for that particular problem. But the units can change depending on the order. Renee McCormick actually had a really good strategy. If you look at the overall order of the reaction and then drop a finger, so say if we had an overall order of 3 and you drop a finger, you're left with 2. The units for K, it's going to be molarity squared. If you had an overall order of 2 and you drop a finger, then the units are just the molarity per whatever time unit that is. And I'll do some examples with you so you'll see what I mean when we go through that. So here we go. The overall order of a reaction is equal to the sum of all of the exponents. So you could have a rate just like this, equal to K times the concentration of your first reactant times the concentration of your second reactant times the concentration of your third reactant if you have one, and they're all to some exponent. Now the exponent isn't always clear cut and dry what it is, so we have to usually figure that out. That's determined experimentally, but it does give us some important information about what happens in our reaction. So zero order, let's say that the concentration of A, that exponent was 0. Anytime you have a exponent of 0, you get 1. So if you tried to double your concentration of A, nothing would happen to your rate because it would just end up being 1 times whatever your rate is. Your rate would stay constant. So we can say that in a 0-order reaction, the rate is equal to K. In a 1st-order reaction, you've got to the 1st power. So if the concentration doubles, then the rate will also double. If the concentration triples, the rate will triple, etc., etc. So it's not equal to 1 at that point, but you get the idea. For a 2nd-order reaction, if the concentration doubles, then the rate quadruples, right? 2 squared equals 4. If the concentration triples and we square it, then the rate goes up by a factor of 9. If the concentration quadruples, the rate goes up by a factor of 16, etc., etc. Whenever it's 2nd order, it's referring to our exponent as 2. Okay? So, let's do an example. When we're using lab data, we typically want to look for things that are held constant, right? We are comparing the concentrations to each other in order to determine the order of the rate, right? So let's do each of these in different color. What am I drawing in currently? I'm currently in orange. Okay. So I want to look and I want to see what the rate of bromine is. Okay. Well, here I can tell that this doubles. That's good. When bromate doubles, I want to make sure that everything else is held constant. And sure enough, that is constant. H plus is constant. Now I can look at my rate. What happens to my rate? Well, if you don't believe me, it does double. Let's check in our calculator. Right? So 8.0 times 10 to the 4th, that's the same as 0.0008, right? 1, 2, 3, 4, yep. Times 2 gives us 0.0016, which is 1.6 times 10 to the 3rd. All right, so this doubles. Cool. So when bromate doubles, the rate doubles. All right. Is that going to be 0, 1st, or 2nd order? You should have said 1st. It is 1st order, right? Okay, let's choose a different color. Let's see. Let's do blue. All right, well, with blue I can see that bromate's held constant here, H plus is held constant here, and bromine doubles here. So let's compare this rate. Okay, 1.6 times 2 is 3.2. With bromine, the concentration of bromine doubles. The rate also doubles. This is, you should have said 1st order. This is also 1st order, yes. And then the last one. The last one's tricky, right? Because we want to hold things constant. Let's choose purple, okay? Well, I see that here, bromate stays the same. It's 0.1 and 0.1. I also see that here, bromine, the bromine ion is 0.1 and 0.1. So those two are held constant, and now we're looking at H+. So here, H+ doubles. So when the concentration of H+ doubles, what happens to my reactant? Well, 8.0, what's 8 times 4? Well, 8 times 4 is 32, so 3.2. This one here quadruples. Interesting. So if the concentration doubles, but the rate quadruples, what is the order of H+? The order of H+ is 2. It's 2nd order. So here they want me to determine the order for the three reactants. We just did that. We've got first, and second order. All right, so if I was to write my rate constant, the rate constant would look like this, right? We've got rate equals K times my bromate times Br minus and H plus squared. Okay, just like that. Now it also wants us to find the overall reaction order. How do we find the overall reaction order? It's the sum of my orders. So we got 1 plus 1 plus 2. Overall, it's fourth order. Fourth order. Okay, so that's pretty easy, right? But then the last part, they want you to figure out the value of the rate constant. Oh man, how are we going to do that? Well, the nice thing is, you now know that since the rate is equal to the concentrations of your reactants times K, and since you have those concentrations in your table here, and you have a rate, you can pick any one of those four, plug in the corresponding concentrations, and determine the K value, right? So we know that, sure, let's go with this one. 8.0 times 10 to the negative fourth is equal to my K, and times 0.10 is 0.10, and times 0.10, be careful, this time it's squared. Okay, so if we were to solve, overall this is K divided by 0.10 to the fourth power, right? You can do simple math there. 0.10 to the fourth. All right, and oh, I forgot to open up my calculator. Okay, hold on. Let me go to my calculator there. All right, or that 8.0 negative 4 divided by 0.1 to the fourth. Oh, look at that. That's easy enough. So our K is equal to 8. Okay, now we need to figure out our unit for K. So we know that our rate is in units of molarity per second. So I know that I've got a molarity times a molarity times a molarity squared. And all of this is times my K. So let's simplify. This is the same as K times m to the fourth. Okay, we know overall we're fourth order. Like we said before, if we take our overall order, which is 4, we drop a finger, we're left with 3. Then K must have units of m to the negative 3. This would cause it to cancel out with m to the fourth, so that we would just have one m remaining. So m to the negative 3 times seconds to the negative 1. All right, so we could say m to the negative 3 seconds to the negative 1. Now, if you're not familiar with that notation, this is the same thing as saying 8 over molarity times seconds. I'm sorry. Molarity cubed times seconds. Okay? And And when we multiply K times our concentrations, it would cause your molarity cube to cancel out, and you'll be left with some number per seconds. The constant's sole purpose is to cause units to cancel out. So that's why we have it. Okay. Next one. This one says write the rate law for ammonium ions and nitrite, and that yields nitrogen gas and water. Okay. So again, we want to look for areas where things are constant. All right. So here I see these are constant, and ammonium doubles. So here it doubles, and if we look here, what happens? The rate doubles. Yeah. So what order is it going to be for NH4? NH4 is going to be first order. So we've got K equal to NH4 plus, it's first order, so I'm just going to leave the exponent as is. Okay. Now, you don't have to pick just those first two. You could also look here and see that 0.02 times 2 gives us 0.04. That doubles. Here, 10.8 times 2. It holds true all the way down, as long as we hold that first reactant constant. Okay. Now, here, if we look here, NH4 is constant, but if we look at NO2, here this one doubles. Let's check the rate. What happens here? The rate also doubles. What is the order for NO2? NO2 is also first order. So, easy peasy, our rate law is going to be K times NH4 plus times NO2 minus. We don't care about anything in the product side because we're only looking at the rate of disappearance here. Okay? Pretty easy. All right, last one. So here we've got this interesting cobalt complex. And in this complex, a cobalt chlorine bond is replaced by a cobalt water bond, actually, OH2. I guess it gets hydrated? That's interesting. Okay. So I have only one reactant, but that's okay. We can still figure out our rate from this. All right, let's look. From here to here, this doubles. Okay. What happens to my concentration? It also doubles. What is the order for my complex here? Complex is first order. All right, it's a first order rate law expression we're going to be looking at. So we know that the rate is equal to K times this weird cobalt complex. I'm not going to worry about how to name this now. We'll get that over with later. All right, that's first order. Good. And then it says it wants you to calculate the value of K. Well, all we need to do is plug in our rate is equal to K and our concentration of 1.0 times 10 to the negative third. All right. And we want to divide that out. 1.0 times 10 to the negative third. 1.0 times 10 to the negative third. Okay, well 1.3 divided by 1.0 is still going to be 1.3. So we've got 1.3. And 10 to the negative seventh and 10 to the negative third, that's a difference 10 to the negative fourth. Okay, so K is equal to 1.3 times 10 to the negative fourth. Now we've got to figure out units. So we have to be careful. Our initial rate is in molarity per minute. That's what that's saying. Molarity per minute. Okay. So if this is first order, that means I'm looking at just one concentration with units of molarity. All right. So my rate constant if I want my rate constant to multiply and end up giving me units of molarity per minute, what does the rate constant have to have units of? That's right. It is just per minute. That's it. 1.3 times 10 to the negative fourth per minute. That's all. Not too bad, right? Right? Because I've got concentration of molarity here, and I want to end up in molarity per minute, so this times a molarity would give me molarity per minute. All right, cool. My last one. All right, so I've got 5 different experiments here. I've got initial rates for 2 reactants. Okay. Well, sometimes they give you misleading information, which is nice. Like right here, look at this. It goes from 0.5 to 0.75. That is not very helpful, right? I don't really need that information, but let's try and find things that show us where A is doubled, okay? So here, A is doubled. Let's look at my rate. Oh, look at that. What happens to my rate here? The rate stays the same. Uh-oh, that should be a big key. Big sign. What is the order for A? All right. A is going to be 0 order. All right. I'm putting it in here for now, and we will simplify in a minute. It's going to be 0 order because the rate does not change. I could double that thing. I could quadruple that thing. I could multiply it times 100 times. It doesn't matter. It's not going to change my rate. It does not affect the rate of my reaction. Okay. And it was nice that we were able to look at these things being held constant and the rates also being held the same. So let's look at one where the rate doubles. Okay, let's look at the difference between 1 and 4 because the concentration stays the same for A. Even though we know it doesn't have an effect, we don't really need to look at it anymore. Concentration stays the same for A, and for B it doubles. Okay, so from 1 to 4, what happens to my rate? The rate doubles. What does that mean about the order for B? B is going to be first order. Okay. Now remember that A to the 0 power is the same thing as 1. So I'm going to simplify that and say that my rate is equal to K times the concentration of B. That's it. There you go. I found my rate. All right, my rate law is K times concentration of B. Now, just like we did with the last problem, let's figure out what our K constant is. So we can pick any one of those things. 0.50 times 10 to the negative second. I just like going with the first one because it's easy. It's right there. K times 0.20. All right, if we divide out 0.20, 0.20, right, we should get that K is equal to 0.25 times 10 to the negative second, right? Which would be, actually, is that right? I'm sorry. Let me check that. 0, come on calculator, 0.50 e negative 2 divided by 0.2. We get 0.025. All right. Yeah. 0.025. And I need to check my units. Let's see, let's go back to my original rate. The original rate is in moles per hour, right? And if this is first order, and I drop a finger, that means I'm not going to have any molarities in my K unit, but I do want to end up in hours, so this is going to be 0.025 per hour. Okay. And I think that was it for this particular lesson. So with the quest, you will have to compare these two things, right? Compare your experimental data. If you see that it doubles, if their concentration doubles and that your rate doubles, it is often first order. If the concentration doubles and the rate quadruples or something to that effect, it will be second order. If the rate doesn't change at all, as we saw with the concentration of A in this problem, then it is zero order. Okay? Alrighty, have a good night.